that's where that term dehydration comes from. Okay, we'll talk about some of the other definitions or terms that we could label on this in a second, okay, or at the end of this. You're going to start with your 4-cyclohexanol. To initiate this reaction, to actually get it to function well, we're going to have to add an acid catalyst. So there's two catalysts that we end up using, phosphoric acid and sulfuric acid. Okay. We don't use solely sulfuric acid because sulfuric acid has a tendency to burn things, much like your skin, so that if you added it to your organic mixture, you're probably just going to burn the organic mixture and you reduce your yield. So we add another concentrated acid in its place and add a little bit of sulfuric acid just to kind of help out with the reaction, but nowhere near as much. That way we can limit that charring effect. Okay? So a little more details about the reaction itself. As with all reactions, we should go through and identify the bonds broken and the bonds formed in the reaction. So we'll compare across reactants to products. We need to find out the bonds broken and bonds formed. What bonds were broken? We've got that OH bond was broken. Is anything else broken? Okay, I hear the carbon-carbon double bond, and by broken you mean formed, right?
Yeah, on the right side.
We've formed the carbon-carbon double bond on the right side, and that's not all that's happened. We've also lost a hydrogen. Okay, it's a bit pesky and irritating because it's an implied hydrogen. Okay, how would you know that that hydrogen has been removed? Well, there's two ways to go about doing it. One, you've seen the reaction enough, or you've worked enough problems that you realize that hydrogen has to get removed in this process. The other way to look at it is, instead of just looking at the structures given, make sure that you draw every single atom on each structure. And if we take a look at carbon-2, okay, without that hydrogen there, how many bonds are shown? 2, which means there's 2 more bonds, 2 implied hydrogens. If we take a look at carbon-2 in the product, how many bonds are shown? 3, which means there's only 1 bond to a hydrogen, which means in the process of this reaction, we had to break off one of those hydrogen bonds. Okay? Or we had to break off one of those hydrogens. Okay? We'll go through the mechanism at the very end of this. So now that we got a general idea of what's happened, we're also going to want to evaluate how we can isolate our product. The goal is to make it and isolate it. Okay? So we can go through and start to apply the knowledge that we've gained from the previous experiments on how we would isolate things. So what's a possible isolation technique? What's that? Reflux allows us to add heat. It doesn't isolate. Distillation. When does distillation work? What does distillation separate? Try again. Liquids from liquids, and it separates them based on their boiling points. Okay? Let's throw out all the options out on the table, and we'll see what happens. Okay? So let's go back and look at the physical phases of our starting material and our product and try and determine if distillation is even a valid technique. Okay? So we could go through and evaluate our starting material. What intermolecular forces do we have in our starting material? What's our strongest one? Hydrogen bonding, because we have a hydrogen bound to oxygen, nitrogen, or fluorine. Would we expect that hydrogen force to be the primary interaction for this compound? No. Why not? You have to evaluate the rest of the carbons in the structure, the rest of the structure. Okay? So in that case, remember, 4 carbons or more destroys a hydrogen bonding interaction. So if we look at the rest of the structure, we've got 7 other carbons, which means our hydrogen bonding effect is fairly minimal on the overall solution properties, and we're looking at the dominant force being London dispersion. With weak London dispersion forces, what phase might we predict? Okay, one of our higher order phases, either gases or liquids. If we go over and look at our product, what do we see over there? London dispersion forces, and that's it. What phase would we predict? Liquid or a gas. So now we could go through and start to pull at some of our other knowledge about the reactions we've done so far this semester. Have you done anything where you've tried to isolate or react something in the gas phase? No, and in fact, the only lab where we tried to do that, what did we end up deciding? To not do it because it was too dangerous. So what are the odds either of these two species are gases?
Very low.
Very, very low. So we're probably looking at liquids. Okay, so that could work. We can look at it using a distillation technique to separate these two liquids. Okay? We could try and do something more simple by doing an extraction. But if we look at our intermolecular forces are pretty much the same. So we wouldn't expect a huge difference in solubility. Okay, so we're going to have to rely on distillation or a difference in boiling points. Which of these compounds would we predict to have the higher boiling point? Probably the one with the stronger intermolecular forces. Which one has the strongest intermolecular force? The one with hydrogen bonding. Our starting material has a higher boiling point, so if we tried to distill, what's going to end up happening? Your starting material will stay in the reaction. What happens to your product? Evaporates, and you can distill and collect that somewhere else. How else could we have approached this? No, even easier. I made you go through and derive that distillation would work based on intermolecular forces. That was a whole lot of effort. There's an easier way to do it.
Look at the boiling point.
You could go through and look at the boiling points, hence the blacked out boxes. So you didn't immediately jump to that answer. Okay? And sure enough, we look at the actual results of our boiling points, and all of our predictions were true. We're looking at two liquids. We're looking at drastically different boiling points. Okay? Complications that we might see coming out of this. What's the boiling point of your product? Okay, 100 degrees. What's the boiling point of the other product? The other product is water, which has a boiling point of 100 degrees Celsius. So when we go through and do the distillation, sure, we can separate our product away from the starting material. Okay? But are we going to get pure 4-methylcyclohexene?
No.
No, we're also going to get water coming across with it. Okay, so you need to be aware of that issue. So when we go through and do the distillation, okay, it's going to serve two primary purposes. One, it's going to help purify our product away from the starting material. So that's pretty nice. The other thing it's going to do is drive equilibrium towards the products. How does it drive equilibrium towards our products? If we go back to our balanced equation, what's wrong with the equation given here? For it to drive equilibrium towards our products, what do we need? We need equilibrium. Is this an equilibrium reaction according to this reaction? No. Okay. So when they built the slide, they forgot to mention that this is an equilibrium. Okay. What happens if we remove product if we're at equilibrium? Pushes to form more product. Okay. So that's going to help us drive our equilibrium, drive our reaction towards our products. Okay. We just discussed how our product is going to come out first. In fact, both products, our alkene, organic product, and water are going to distill out. What we can end up doing is using that Hickman head, which has a nice little side port on it, okay, with your little cap, and you can stick a pipette in and pipette that liquid out of the side port. Okay. What's that?
We didn't do that in lab.
Do your Hickman head not have a side port?
No, we just have enough time for distillation.
Yeah, we just attached it to the water condenser.
Oh, well, why didn't you tell me you didn't do a distillation?
We just did the water
You just did.
condenser, like,
Yeah, we did a water condenser.
Okay, so
we omitted that part.
yesterday's section wasn't very nice then because they didn't tell me they didn't do a distillation. They were all happy with it. So, new glassware setup then. So let's take a look at this. You've got your reaction occurring in the conical vial at the bottom of this flask. Okay, we can then attach that to the Hickman head, which is that weird shaped thingy. Okay, your gas rises up inside, condenses on the side, drips back down, and collects in a very now illegible thing. So let's erase that. Collects down there. What you can then do, because most of your Hickman heads have the side port. It's just a little arm coming off the side with a nice little plastic cap on it. You can pipette the liquid out that side. Okay? That liquid will be your product, alkene, and water. Okay? The rest of the setup you're familiar with? Okay, questions now about the setup. You guys okay with that? Sorry, I totally thought you guys had seen that. Okay, so once you collect it, you're collecting your product and water. You'll probably get a little bit of phosphoric acid coming across too, just because the acid likes to mess with things that transfer around. Okay? We need to come up with some way to separate these. Okay? What's the first way that you might say you could separate them? What's the structure of 4-methylcyclohexene? What intermolecular forces do we have? London dispersion forces. What does water have? Hydrogen bonding. Would we expect those two to mix? No. So we could expect to see two layers form immediately from our reaction mixture. But due to the presence of heat and the slowness of the distillation process, we end up forming an emulsification, or said more simply, salad dressing. Okay? The water and your organic product completely mix. Okay? And we end up with a very cloudy solution, okay, or you might end up with a cloudy solution. How can we force two layers to appear? We can add something to it. What should we add? And you got the right idea on shifting towards that first statement, but we're going to focus on add and then aqueous. Sodium chloride's irrelevant for this first part. What are we adding when we add aqueous? We're adding water. We're adding more of one of those layers to help force the separation. Okay? Why don't we add, say, an organic substance, say diethyl ether? Like dissolves like, so the diethyl ether will dissolve your organic product. That's fine. You still get two layers. Why do we not add ether?
That's the stuff we want. We don't want to mix it.
So it adds an extra evaporation step, but diethyl ether has a really low boiling point, right? 35 degrees Celsius. So we could just leave that out. The ether evaporates off. We've got our product. So that's not a huge barrier to that.
Water's cheaper.
Nail on the head. Water is cheaper than your organic compounds. So why do we add water? It's cheaper. Okay? It's also less dangerous. If we've got ether in the room, you're going to be releasing those ether vapors, exposing yourself unnecessarily to organic compounds, increases the hazards in the lab. So it makes sense to use the cheapest, safest option possible. Okay? Well, notice that you're not adding just an aqueous solution. You're adding an aqueous solution of sodium chloride. Why do we add the sodium chloride? Why not just add water? No, sodium chloride is just a salt. It's not really going to react with the phosphoric acid. If you're out trapped on a boat, out in the ocean, dying of dehydration, you're thirsty, 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 what do they tell you to not do? Drink the salt water. Why not? It dehydrates you faster than if you didn't drink it. Why? Water's going to track to the salt solution. So as you ingest the salt water, water from your body goes into your stomach to dilute the salt concentration. We're relying on that exact same process here. Okay? When we add that salt solution, water's going to drive into the aqueous layer to dilute the salt concentration. So that helps us further separate those two compounds, our organic from our aqueous. Okay? At that point, we can pipette the two liquids away from each other, and we'll have our product and probably trace amounts of water. How can we get around the trace amounts of water? We add a drying agent, also known as simple. Easier than that. A salt. Okay, why? Our very first step was to add aqueous sodium chloride. The sodium chloride is a salt. What was its role? To remove water. What happens in our second step? We add even more salt. Our salt concentration is even higher in this case because we're adding it as a solid. So it can remove the last remaining dregs of water out of our solution. We'll now have our solid sodium sulfate salt trapping water with our liquid product around the outside. How do we separate those two? We could do a filtration, or we could do just decanting, something simple. At that point, you've got your final product, so we want to characterize and prove that you got it, so we can go through and do IR and bromine tests. We've already done the bromine test or talked about it a few times, so I won't go into it in detail, but your product has an alkene. When we add bromine to it, what happens? The bromine reacts. It's no longer present. If the bromine's not there, what happens to the color of our solution? It stays colorless. What happens if we added bromine to our starting material? Shouldn't react, so what happens to the color of the solution? It should kind of dilute a little bit because our concentration is changing for our bromine, so we're probably going to see kind of a yellow, reddish-brown solution. Okay? You should test both your starting material and your product. Why test them both? You need a control. You need something to confirm that the result you're seeing is actually a valid result. If your starting material had already had a double bond, what would happen? It would decolorize. So what does that mean about the effectiveness of the bromine test? Not very effective at all, and it wouldn't be something you'd use. Okay? So the idea is you need to understand why we're doing these tests. Does it make sense to do them or not? Okay? Next thing we can go through and do is look at IR spectroscopy and use IR to identify your compound. Okay? As with all IR problems, particularly like your practice exam, your last exam, you should go through and identify all the bonds that are present in that structure. If you identify all bonds, you've covered your bases for everything that we could possibly ask. So we can go through and look at 4-methylcyclohexanol. What bonds do we have in that structure? We get OH. What else do we have? We have CHSP3. What else? We have carbon-carbons. What else? We have the carbon-oxygen bond. Anything else? No. So then we can move over to our product. What do we have in our product?
CC double bond.
What else?
CHSP2.
What else?
CHSP3.
If you could say that a little bit more in synchronicity, that would be awesome. That was not very synchronous. Okay? Now that we've got all the possible bonds, we can go through and just look for the differences. That's all these types of questions are asking. When we ask IR, it's what's different between these two lists. Okay? So we can go through and say, what things are different? The OH is different. What else is different? CO is different. What else is different? Okay? Now that we know our differences, now we can go through and look up the tables of data and say, do I know where these things should show up? Of those 4, only 3 of them you're officially responsible for. You're not officially responsible for the carbon-oxygen single bond because it shows up in the fingerprint region. Okay? So the idea is to identify these important differences because those differences are what's going to drive your answers. Okay? So at that point, you can conclude everything, wrap everything up, all sorts of fun, look at your yield, that fine stuff. So let's go back and look at the chemistry a little bit. Okay? In the process of dehydrating alcohols, from what I understand, this complete reaction doesn't show up until second semester. Okay? So it's right at the very beginning, but you're looking at similar mechanisms. The other names that will show up for this type of a mechanism are elimination and beta elimination. You might also see dehydrohalogenation. They're all ultimately looking at the exact same thing, the removal of a small molecule from another one. Okay? And in the process, we end up forming a double bond. When we look at the dehydration reaction, we can go through and say, okay, yes, we lost the OH and we lost a hydrogen. Okay? So what we want to do is come up with some more information within that. You'll notice that one of the names that we could come up with is beta elimination. So it might be nice to know where this beta is coming from. Well, name this compound for me as best you can. How many carbons are there? What's that? This compound here. How many carbons are in that structure? 2, which means ethyl. We don't know what those other lines are, so we're leaving that out of it for the moment. Okay? Ethyl. So we could stick with ethyl, but we're all single bonds, so we would then call it ethane. But we have an alcohol. This is the part that in theory you guys don't know. If you have an alcohol, we change the ending to all. So we end up with ethanol. To be extra specific, let's specify exactly where that alcohol, or OH group, is in that structure. What position is it located at? Position 1. We're looking at nomenclature. Okay, why do we not say position 2?
Because it's the largest. Substitute.
We want the lowest number. Okay? So instead of going by alpha or calling those positions 1 and 2, because the 1 and 2 are used for nomenclature, what we're going to do is develop a new system. And that's going to be using Greek letters. Okay? So position 1 in our Greek alphabet would be alpha. If we move to position 2, we get beta. So when we're looking for our beta elimination reactions, we find the group that wants to leave, okay, our most polar atom, our leaving group. Okay, we'll call that position alpha, and we'll go to any carbon that's immediately attached to it. That is now a beta position. Okay, if that beta position has hydrogens, we can eliminate. So if we go down and now look at your examples down below, beta position right here. There's that hydrogen that we removed. Where else is there a beta position? I like the head nod. Directly up. There's a beta position there. Where else do we have one? To the left. Yeah, okay. Do we have hydrogens at those positions? Yes. Can we do the beta elimination to those positions? Yes. Why did we not show those eliminations? What's the difference in the product? There isn't one. We'd get the exact same product if we eliminated the hydrogen from any of those beta positions. So why should we not bother to look at those? Because it gives us the exact same result. What happens in the bottom case? Where else do we have beta positions to my leaving group? We've got that one. Where else? And do the head nod up. Do we have a hydrogen at that position? Yes. Why did we not show that beta elimination? Produces the exact same product. Okay? So these would be our simple examples. Okay? One of the things that we have to do before we can initiate our elimination reaction is activate the alcohol. That OH is not a good leaving group. If we tried to have that leave on its own, what would our product be? We would have R positive because it lost electrons, and then OH minus. When we're looking at leaving group ability, we can pull a face test on it. Okay, R positive, you probably don't know anything about that. That's fine. So let's look at OH minus. Do we really want OH minus splashed in our face? No. That's a strong base. If it's highly reactive, and what is that going to mean about that process actually occurring? It's not. Okay? So what we've got to do first is activate the alcohol so that it can act as a leaving group and actually leave the structure. To do that, we evaluate the reactivity of the alcohol. It has lone pairs, which means it can act as a base, which is a proton acceptor. When it accepts that hydrogen, we end up forming this species. Does oxygen want to be positive? No. So what does it do? It steals electrons from where it can get them. In this case, what we're looking at is hoping it's stealing them from that R oxygen bond. And we get our leaving group. What would be the product if that left? We get our R positive, and how reactive is H2O? Face test. Are you really concerned if we throw water at you? Okay. It just depends, I guess, what you're wearing and how cold it is. Okay? You have feelings, yeah. So what we're going to go ahead and do is take a look at a mechanism real quickly. So, you guys, please say that didn't do it. So let's draw out our possible mechanism here, because I want to go through it slowly at first. We'll start with our alcohol, and we're going to add acid. For the sake of simplicity, I'm just going to say it's H+, because our strong acid supplies H+. Okay? So what's the most reactive thing in this first step? What are you most concerned about? Are you concerned about alcohol or acid? Probably the acid. Okay? What's wrong with the acid? Why is it reactive? It's positively charged. So what do we need to do to stabilize a positive charge? Give it electrons. Where do we have electrons? On the oxygen. So we can share our electrons. What happens? We get our H2O as a potential leaving group. Our oxygen is now positively charged. Does oxygen want to be positive?
No.
No. So what is it going to do?
Steal.
Steal electrons. Where does it steal electrons from?
From the bond.
Which bond?
The one right there. The carbon.
No.
Oh, no.
What's the easiest bond for it to get electrons from? From the hydrogen. Why the hydrogen, not the oxygen? Our carbon is more electronegative than our hydrogen. We would expect the electrons to be stolen from the hydrogen preferentially. What does that mean for the reactivity? We go backwards. Okay? This is an equilibrium reaction. We have to be aware of those other steps. Okay? That doesn't take us towards our product that we know exists. So now we can go back and say, where else can we get electrons from? Now your answer is from the carbon. Okay? So we can go through, take the electrons in that bond, and give them to the oxygen. What's our result?
H2O.
We get H2O and
Alkene.
our positive charge, right? That positive is our alpha position. What do we need to find? Our beta. Where do we have beta positions? By all those carbons, you just mean those two. I agree. Okay? Do those two have hydrogens? Yes. So we can go in and draw on those hydrogens so that we know they're there. Okay? What happens if we eliminate each of those hydrogens? Do we get the same product? No. Interesting. How do we decide what our product is? Everybody's least favorite thing to do, particularly if you've ever come and asked me for help. You get to draw every single product. Once you've got the products, you can evaluate the differences between them. So if we go through and take a look at our red hydrogen, our product looks something like this. If we took a look at the blue, let me draw on that arrow, take our electrons away, our oxygen comes in, swoops in, pulls off the hydrogen. If we take a look at the blue product, our oxygen can swoop in, steal off the hydrogen, and we form our double bond here, and we get, is this visible? Good. What's the difference between those two products? The substitution pattern around the double bond. Which double bond is more stable? Red or blue? Red. Good answer. Why is red more stable? It is a more substituted double bond. How many substitutions does that double bond have? 3. Where are those 3? 1, 2, 3. This is tri-substituted for our double bond. If we take a look at our blue one, where are substitutions? 1, 2. Okay? So when you're looking at multiple beta products or multiple beta positions that generate different products, you've got to form the one that forms the most substituted double bond. Okay? If you've got questions about the activity, raise your hand. Raja or I will come by to help you out. Or if you've got questions about the lecture.